In this video, we're going to talk a little bit about completing the square. Sometimes it's useful to use the technique of completing the square to transform a quadratic or second-degree polynomial into the form of a binomial squared plus a constant. If the integrand is a quadratic polynomial, then this will put the integrand into a form where a trigonometric substitution may be helpful. You should have seen the algebraic technique of completing the square in your pre-calculus courses, maybe in algebra class or pre-calculus. However, let's spend some time reviewing completing the square and related concepts first, and then we will apply these techniques to finding some integrals via trigonometric substitution. So completing the square consists of changing a quadratic polynomial of this form, ax squared plus bx plus c, a, b, and c are constants, into the form a times parentheses x minus h squared plus k, where a, h, and k are constants. Actually, a is the same constant. H and k will be different constants. For the purpose of finding antiderivatives, we want to put this into the form c times parentheses x minus h squared plus or minus a squared, or c times u squared plus or minus a squared, so that it works like we did before in trig substitution, as we saw in our last video. So why is it called completing the square? And the reason is that the critical step involves taking a quadratic polynomial of the form x squared minus 2kx and adding a constant to it so that it becomes a trinomial square, factoring as x minus k squared, a perfect square of a binomial. We can visualize this process with algebra tiles or rectangular representations of quantities and variables. The following three GeoGebra activities demonstrate that critical step. And you should open them and experiment with the controls to explore these concepts. These are dynamic illustrations. You really have to see them in action to get their full benefit. So let's look at this first one here. Let me go ahead and just open it up from here. So here's the activity that Tim Brzezinski wrote. So if we have x squared minus 16x plus some constant, or let's start with the positive one here. Let's start with 9. Okay, which we can change by the slider or by typing in. So this box here represents x by x. So this length is some unknown x. It looks like a specific number right here, but it doesn't really matter. It can be any variable size. Okay, and then we have to put the 9x squares in there. So each of these little bitty squares is a 1 by 1 square. So the 9x is going to be a 1 by 9. An x by 9. Sorry. It's going to be a 1 by x or x by 1 rectangle, and we have 9 of them. So we're going to build those in, and what we're going to do is, actually, let me start with an even number. Let's put 4. We can do it with an odd number, but let's start for the first example. Let's do an even number. So we're going to put 4 of them, and the idea is you split half and half. You put 2 of them on this side and 2 on the other side. So this side right here is x. So this is 1 by x. This is 1 by x. This is x by 1. But those are the 4 x's there. And notice that we've almost got a big square, but we're missing a piece right there. So what you want to do is take that, pull that into a square. How many little squares do we need to complete the square? And what's the answer? Well, if you count them there, that's 4. And sure enough, there are 4 there. It tells us if we get it correct or not. Okay, so let's go back. Let's do another one. What happens if let's do 9 like I started in a minute ago. Then when you put them in, you're going to have 4 x's here, 4 x's here, and then you're going to have a half of an x here and a half of an x here. So you have to split those up, which means you're taking half of this guy in the middle right here. Okay, so how big is this square right here? Well, it's however long this is by however long this is. Well, it's the same length both ways. So that's 4.5 times 4.5. So what you're going to do is you're going to take the half of this coefficient here, put half here and half here. You're going to square it to find what you need to complete the square. Okay, so that's 9/2 square. Okay, so that would be 81/4. Okay, a little easier to see when it's an even number, but it doesn't matter if it's not. If it's a negative, the way this one does it, let's go to -6, let's say. This particular illustration just illustrates those as red things. We're actually subtracting 6x's, but as far as the algebra of it right here, it's going to work out the same. There's actually 9 of them there. So you're still taking half of this. Now, if you think of this as a -3 times a -3, that's still a +9 there. So we're still adding 9 at the end. Okay, so that gives you an idea of why we call this completing the square. You're completing it so this factors as x minus 3, which is this x and then the -3 squared. Okay. All right, let's take a look at this next one. Let's see. Similar thing. This is actually the same thing over here on the left, but it also puts something else on the right here. It's going to show how this goes to a graph, and it's going to show a little bit of the work here. So if we start sliding this, let's see what we're going to do. We're going to take half of the 6x, put 3 of the x's here and 3 of the x's up here. So there's the 3, there's x, there's 3. And so this is going to be 3 squared right there, which is 9. Okay, and then if you graph the completed square, it's x squared plus 6x plus 9, or x plus 3 quantity squared. Here it is here. And the x plus 3 gives us a root of -3, or an x-intercept of -3, 0. It's squared, so that's going to be the vertex. And then when you square the -3, you're going to get a y-intercept of that -3 squared, or the +3 squared, either way you look at it. And you get 9 here. Okay. Here's another one. Let's take a look at this one here. Saving here. Okay, thanks to these different people who have put these algebra applets for us together here. Okay, so this one's going to show you a little bit of the algebra that's going on. So if we have x squared plus 10x, and let's say equals 39, so we've got it in the form of an equation. And we can change these numbers here. Let's see what happens as we slide this. You sort of pull these down, and you can see the x squared here and the 10x here. We want to split the 10x in half as 2 5x's. Completing the square gives us the 5 squared there. So what do we do with that? Total area is x plus 5 times x plus 5. So it's x plus 5 squared. It's got to be the 39 plus the 5 squared that we added. So what we did is we added 5 squared, or 25, to both sides of this equation. The part on the left factored as a binomial squared. This is a trinomial square once you add the third term. Factors as a binomial squared. And that just changes the constant on the other side here. Now, if we want to continue on to solve this equation, we can solve an equation like this by completing the square. We just have to combine the like terms on this side right here, 25 plus 39 is 64. Take the square root of both sides. That gives us the absolute value of x plus 5 on the left and the square root of 64 on the right. Get rid of the absolute value by putting plus or minus here. So you can do that one step by square root of both sides, but putting a canceling here, but putting a plus or minus here. Square root of 64 is actually just 8, right? So this is then subtract 5. So negative 5 plus 8 would be 3. And negative 5 minus 8 is negative 13. So you could check those two numbers by plugging them in here and making sure that they work out. And so this one gives you a way to work through this. We can change this to some different things. Let's see what it does here. If you put in, we can put in an odd number here, 5. It's okay. Put in, say 10 here. Something different. Just see what happens. See how it works with that. So those are 2.5x by 2.5x. That's 2.5 squared. It's running off the page here, but that's 2.5 squared. Okay, which is 6.25 plus the 10 is 16.25. You get negative 2.5 plus or minus that square root. Okay, I'm just kind of curious what it does with a negative here. What if I put negative? Negative 6. It may not illustrate it. Yep, it's not allowing me to put in a negative there. But the same process would work even though the illustration might not be exactly the same. Oh, actually, this one does. This one requires a positive, excuse me. But this same illustration, if you go down, this one here allows a negative. So you put a positive number here, but there's a subtraction here. And this one has a different illustration for the negative. So let's look at that. Let's just do the one they have, 4 and 12. So you start with starts the same way, right? This one's interesting. Here you start with an area of x squared. Here you have 4x. We want to split this in half, but this actually is subtracted from this x squared. So we take that over, subtract it from the x squared, and you're left with, well, this has got to be 12 of what's left over. That's what it says. Now, you take the 4x that's empty here, split it in half, and bring that across. And there's your completed square there, is adding that. So it's an area that's subtracted. So look at however far across this is, okay, which is 2, right? And we're going to subtract that from here. Move that up. So this is x minus the 2. This is here's the x, and then we subtract 2. And what's left, and that shaded area has to be 12. What's left is the part we have to complete the square, which is a 2 by 2, which is 4. So we're going to add 4, 2 squared to this side and this side. When we add 2 squared to this side, this factors as x minus 2 squared. And then we add 2 squared or 4 to this side. So that's going to put 16 on the right. And then square root, we get x minus 2 equals plus or minus the square root of 16. Add 2. So our answers are 2 plus the square root of 16 and 2 minus the square root of 16. Square root of 16 is 4. So 2 plus 4 is 6 is one of the answers. And 2 minus 4 is negative 2 is the other answer. So this is a different way of looking at it. Maybe a little more complicated than the previous one, but actually probably a little more accurate in the sense that it's actually subtracting areas when we're working through this. There's some static screenshots. All right, here's another one to look at. These are pretty cool. Let's take a look at this one here. Okay, so this one shows the let's load it up. This one shows step by step the algebra that's going on without showing the visual illustration. So we can change the coefficients like this. Okay, and let's say we change. Let's suppose we have a coefficient here, whatever we want here. We can have a middle coefficient, whatever we want here. And this is going to change, these are going to change some of these numbers a little bit. Okay. And so let's see what happens. Actually, that's not the middle coefficient. You'll see what it is here in just a second. So anyway, we have this set up like this. So what we do is, first thing is we group the x terms together and factor out that leading coefficient. Leave the constant term kind of off by itself. This time we're working with a single polynomial. This is going to be a little bit more like what we're working with in our integrals that we're going to be doing in a bit. So, so we factor that out. Then what we want to do is complete the square on this red part. Okay. So we want to take half of the 8, which is 4. We're going to square it, that's 16. So within that parentheses, we're going to add and subtract 16. So this equals is valid. First one we just did the distributive property, so that equals is valid. And this we're adding and subtracting the same thing at the same level. Now, what I usually do next is group these three and factor it, and then distribute. I think they're going to do it the other way around. Let's see. Yeah, I think they group these three and distribute it before factoring. Okay, so they distribute it here. So it's 3 times that trinomial. And then 3 times this. And now notice this guy right here is always going to be positive, the one that's inside here. The one out here is going to always be negative. As we saw just a minute ago, it doesn't matter whether you end up with negative times negative or positive times positive. That little square that you added is actually added. It's positive. Okay, so 3 times negative 16 is negative 48. Now, a couple things we can do. We can combine the like terms here, and we can factor this part here. So they did both of those things. Remember, this factors as x plus the 4 squared. So that 4 right there was the 4 that was right here. And you add these together, and you get negative 49. Okay? And it's done. It's in the form that we want. It's a times x, say minus h squared plus k. Then h is negative 4, and k is negative 49. Okay, here's another example that I've worked out. Okay, without the app, just me typing it up. Okay, so we want to take y equals ax squared plus bx plus c, put it in the form y equals a, parentheses x minus h squared plus k. So here we group the terms together that have variables, leave the constant term alone, factor out the leading coefficient of the x. If it leaves fractions here or decimals, that's fine. At this point here, we want to take half of that coefficient, square it, add it, and subtract it. Grouping these 3 together, this factors as a trinomial square. It's x plus the 1 square. And these lines didn't line up where they're supposed to be. Let's see. Okay, so what are these lines showing you? It's actually, I'm looking down here, and I kind of do it in this order. Actually, when I'm writing this by hand, I'll write this part down here. I get this part first. I know this is going to be x squared. I want it to be an x here. I want the whole thing to be squared. That middle sign is here, and the coefficient's half of that coefficient. So positive 2, half is positive 1. And I want that to be squared. Well, to square this, what do? You square the first, multiply and double for the middle. We just check that. You square the last. So square the last term, that comes up here as 1. If I add it, I have to also subtract it, and that means it comes down here. So I'm kind of following that flow. Okay, now I'm going to distribute the 2. 2 times this thing here. 2 times the negative 1 is negative 2. Add these together to get 4. And now we have it in the form that we want. H is negative 1, K is 4. Now, so what we've said is y equals 2x squared plus 4x plus 6 could be rewritten as 2 times x plus 1 squared plus 4. So the graph is exactly like the graph of y equals x squared, except that it's expanded vertically twice as far from the x-axis. That's the 2 here, whether it's here or here. So it's taller. And then it's shifted to the left one and down, no, up 4. Not down 4, up 4. Okay, the y-intercept is 0, 6, which you can see from this form. The vertex is negative 1, 4. Okay, and so we have that. We can sort of check that we did it right by putting both versions in our calculator, make sure the tables match, and there's the graph. So negative 1, 4 is that coordinate of that vertex right there. Here's a better looking graph here. Okay. So you can see that. So here's another example. Why don't you try this one yourself? Okay. So now that you've seen a few of these, it's your turn to try one. If f of x equals 6x squared minus 24x minus 16, see if you can answer some of these questions a little bit. First of all, what's the y-intercept of the graph? That should be easy from that one. Y-intercept is a point with the x-coordinate 0, so it's parentheses 0, comma something, and that something is just this constant term, negative 16. Complete the square to get it in the form f of x equals a times x minus h squared plus k. You might want to pause the video in a second to work that out yourself and then come back. Okay, hopefully you're back. Here's the steps. Here are the steps. Group the first two terms and factor the 6 out. 6 divided by 6 is 1. Negative 24 divided by 6 is negative 4. Take half of that is 2. Negative 2 because it's negative. Square it, you get 4. Put the minus here. So then this factors as x minus 2 squared. And then you still got the minus 4. Distribute the 6. 6 times 4, negative 4 is negative 24. Add these together, it's negative 40. What's the vertex? Well, it's positive 2, negative 40, which is right down here. We already said that the y-intercept was negative 16, 0, negative 16, right here somewhere. And check that. So notice that each step of the process was a legit thing that we could do. Okay, so let's go ahead and show that we can do this in general. If f of x equals ax squared plus bx plus c, we can group the first two terms, factor an a out. That leaves b over a for the coefficient here. We want to take half of b over a, so that's b over a over 2 to bring down here. Arrow's got out of whack here again. Square that, you get b squared plus 4 over 4a squared. That's plus, but then we want to subtract the same thing to keep this equals valid. This part factors as x plus b over 2a squared. Distribute the a, it cancels one of these a's here. Okay. And then, let's see. Over here, I need to get a common denominator because these are just constants. We'll put it together. So multiply c by 4a over 4a. So that's 4ac over 4a. Now they have the same denominator. We can keep that and add the coefficients. 4ac minus b squared, or I'm going to say b squared minus 4ac, and then factor a -1 out front. And if you look, we have it in the form that we want. H is actually minus b over 2a, and k is the opposite of b squared minus 4ac over 4a. So we can transform all quadratic functions, f of x equals ax squared plus bx plus c, into the form a times x minus h squared plus k. The only step that could give us any problem is if we were dividing by 0 when we divided by a, but if a is 0, it's not really quadratic to begin with. It's linear. And so this gives us a nice little formula for the vertex. H is minus b over 2a. Now what's k? Well, k is just the y-coordinate that goes with that h. It's f of h. It's also minus the opposite of b squared minus 4ac over 4a, but you can also see it as just f of h, so you can just plug it in, what you get h, plug it in the original form, and then solve for k. That's another way of doing this. Now we could have gotten that vertex formula with calculus a little bit maybe more easily. This was worked out as if we didn't know any calculus. Okay, and this is the way we would do it in a pre-calculus class. But since we know some calculus, we know that the vertex is going to be at the minimum of the derivative. So it's really easy to take a derivative of this. If f of x is ax squared plus bx plus c, f prime of x is 2ax plus b. Set that equal to 0 and solve for x. And we easily see that x is minus b over 2a. So we can use that to convert the following to standard form. So you might practice taking this one right here, y equals 6x squared plus 4x minus 9. You might do this two ways. You might do it by completing the square technique that we did up above, or use our shortcut of knowing the vertex formula. So here's how you do it with the shortcut. H is minus b over 2a, so it's negative 4 over 2 times 6. And let's see, we can cancel a 4 and a 2, and the other 2 and a 6 leaves a 3. So h is negative 1/3. To find k, we just put in negative 1/3 in place of x here and here. And let's see. We're going to square this. This is going to be positive. One of the 3's is going to cancel that down to a 2, and the other 3 is going to stay, so that's a 2/3. This is minus 4/3, and we might get this into thirds too, so that's multiplied by 3 over 3. That's negative 27/3. Add the numerators. Let's see. 2 minus 4 is negative 2, minus 27 is negative 29, so it's negative 29/3. And so now we can put it in the form 6 times parentheses x minus the h, so that's minus a negative 1/3 or plus 1/3 square, and then plus the k, which is negative 29/3. Now, so we're often interested in finding the x-intercepts of something like this, which is, in other words, solving a quadratic equation. We want to take 0 equals ax squared plus bx plus c and solve. Well, we already saw that ax squared plus bx plus c by completing the square is a times parentheses x plus b over 2a squared plus a negative b squared minus 4ac over 4a. So I'm going to add this to both sides, which is kind of why I left that as a minus there. So it just comes over like that. Now, I'm going to go ahead and divide by a on both sides, so it cancels here, makes this an a squared in the bottom, and I switch sides on this here. All right, then what else? Now do a square root, so that cancels out the square here. Technically, it leaves an absolute value and a square root here, but then you can get rid of the absolute value by putting plus or minus here. Now, let's do square root of the top and bottom. Square root of 4a squared is, well, technically it's 2 absolute value of a, but the plus or minus out front takes care of both possibilities anyway, so we get that. Now we're going to add a negative b over 2a to both sides, and now we have that. Notice that's h plus or minus this b squared minus 4ac, which I'm just going to shorten to call d. It's called the discriminant. and we get this over 2a. So this looks familiar to you. That's the quadratic formula. A lot of people will write this as one single fraction, where it's negative b plus or minus the square root of b squared minus 4ac all over one fraction, all over one denominator, 2a. I like to leave it apart like this because each of these parts has a separate meaning. This minus b over 2a is h, that's the x-coordinate of the vertex, and this b squared of b squared minus 4ac over 2a is how much we go left or right of that to get to the roots, or the x-intercepts. And so this gives us the quadratic formula. Where does the quadratic formula come from? It comes from the technique of completing the square. So here we have some review of quadratic functions. The general form is p of x equals ax squared plus bx plus c, and from that we can tell the y-intercept. That could be called the y-intercept form because 0c is the y-intercept. The standard form could also be called the vertex form because we see the vertex very easily from that is p of x equals a times x minus h squared plus k. The vertex is hk, and h is minus b over 2a, comma, whatever p of h is. And the factored form is a times x minus root 1 times x minus root 2. If r1 and r2 are real numbers, then r1 0 and r2 0 will be the x-intercepts. If r1 and r2 are not real numbers, you can still factor it, but you have to go to the non-real complex numbers in some cases there. And that indicates a parabola that doesn't cross the x-axis. The vertex formula is minus b over 2a for h. It's also the average of the two roots, r1 plus r2 divided by 2, whether they're real or not. And here's the quadratic formula that we just went over as well. Okay, so r1 is h plus the square root of d over 2a. In other words, it's minus b over 2a plus the square root of b squared minus 4ac over 2a. And then r2 is the same thing with the minus in the middle. The a is the same a in all three forms, and it opens up, it's concave up if a is positive, and concave down, opens down if a is negative. And here's one written in all three forms. F of x equals x squared minus 8x plus 7. So from that form we can see the y-intercept at 0, 7 right here. It's also equal to 1 times x minus 4 squared minus 9. So 4, negative 9 is the vertex down here. It has symmetry around the line x equals h. So is 1/2 is a mirror image of the other over that vertical line at x equals 4 in this case. What else do we have? We have, it factors it's x minus 1 times x minus 7. So 1, 0 and 7, 0 the x-intercepts. There's 7 and 1 there. The square root of d over 2a turns out to be 3. So there's your h plus 3 to get to that one, and your h minus 3 to get to that root. So that each one of these parts of this has, this part has a geometric meaning, and that has a geometric meaning separately. So what are some conclusions? Every quadratic function is simply a transformation of the standard power function y equals x squared. Thus, all graphs are basically the same shape, like the one above called a parabola. They have very nice formulas for the vertex and x and y intercepts of the graph. We can use these to solve any quadratic equation. The quadratic formula gives us a guaranteed method of factoring any quadratic trinomial into two linear factors, as long as we're willing to have complex coefficients. There are three good forms for the equation, each directly telling us different information about the function. The y-intercept is easily identifiable in the general form, p of x equals ax squared plus bx plus c. The roots and x-intercepts are easily identifiable in the factored form, p of x equals a times x minus root 1 times x minus root 2. And the vertex is easily identifiable in the standard form, p of x equals a parentheses x minus h parentheses squared plus k. And we have straightforward techniques and formulas to convert. I actually should say among the forms because there are three of them. Now, let's stop there, and we'll use this in some trig substitutions in the next video.